Okay, so now we're going to prove something using the algebraic method, which is going to look exactly like every other proof that we've done in this class. Now, I'm going to follow the example in the book. For no logical reason I can discern, they switched and used a different example and then come back to our original example. So we'll do the same thing because I'm not a creative man. So what they wanted to prove was Q minus P and R equals Q minus P intersection Q intersection R. So they want to show that those two are equivalent. And we'll start by Q minus P and R, which remember is the same as Q and the complement of P and R. Remember, in sets, when we say the complement, that is the same as the negation. We can then apply De Morgan's rule, and we'll get Q intersection P complement union R complement. Then, whenever I see something like this, my natural instinct is to, I should write over on the side De Morgan's law. My instinct when I get to this point is always to distribute it. So I'll get Q intersection P complement unioned with Q intersection R complement. Now, if you were doing this as a straight problem and you started at the top and you were working to the bottom, you would have a real hard time figuring out what to do at this point. Usually, the best way to do an algebraic problem is to kind of work it from both ends. And we're going to do it. So we're going to leave this in this format, and then we're going to go and start working from the bottom up. So remember, our other side was Q minus P intersection Q intersection R, which is the same as Q intersection P intersection Q intersection R, and we take the complement, which per De Morgan's law is the same as, I'm going to move over a little bit, Q intersection P complement union Q complement union R complement, right? And just like before, we can now distribute this, and we'll get Q intersection P complement unioned with Q intersection Q complement unioned with Q intersection R complement. And what should, I should write down that is distributive. And what should jump out at you right away is Q and not Q is the empty set, right? And anything unioned with the empty set is itself. So essentially that drops out, and we have Q intersection P complement unioned with Q intersection R complement. So it dropped out due to that bound rule, right? So the negation rule and the bound rules were both used, and I kind of ran out of room, but you get the idea. So the negation rules and bound rules bring those two together. Now, if you had started from the top and not started from both ends, this would have been really hard to find. Technically, you can use those negation rules and bound rules, so you can always union something with the empty set, and you don't change the actual result. But that's, you know, if you could do that at every single step, how would you know when to do that? So when doing algebraic manipulation, it's always useful to start kind of on both ends and see if you can bring them closer to each other. All right, so that is the example they use in the book. Let's go back to our original example. So if you remember, our original example was P minus Q intersection with R minus Q is the same as P intersection R minus Q. So let's go ahead and start with P intersection R minus Q, which we know is the same as P and intersection R and Q complement. And then down here we have P minus Q intersection R minus Q, which is going to be the same as P intersection Q complement and R intersection Q complement. So if we go back up here, we know we can apply the distributive rule, and we will get P intersection Q complement and R intersection Q complement, which is the same. So I guess that's why they didn't use this example for our original example for the algebraic example, because it's kind of trivial, right? You only do one step. But again, it's a lot easier if we work it from both directions. Otherwise, I would have had to have reconverted this back into the minus format, which would have been harder to guess. Okay? All right, let's do a real quick review of what, and I'm misspelling review here, a review of what we've learned so far in sets, right? Well, we've learned the notation and we've learned some of the definitions for sets, but we've also learned 4 different ways of proving things about sets. The first being the Venn diagram. And honestly, the Venn diagram is probably the best way to prove anything because it's visual, it's obvious, and yeah, it's more intuitive for most people. We learned the element method, right? If X is an element of A, then X must be an element of B, and then we prove it, the other way, and we've proven that 2 sets are equal. The tabular method, which is a truth table, right? It's just enumerating all possibilities. And it's just as useful as the truth tables that we were using earlier this semester. And finally, the algebraic method, which again is just like what we were doing earlier this semester. So we have 4 different tools in our toolbox so far that we can use to prove sets are equal, right? Or to prove that one set is a subset of another. We're going to start using this when we look at ordering of sets in the next section. All right, if you have any questions, ask in the comments below.